In part 6 of this series on general relativity, we're going to put together all the pieces that we've worked so hard to get to. We're going to talk about calculus in GR. We're going to talk about density in GR. We're going to talk about how electromagnetism operates in GR. We're going to talk about momentum. And we're going to talk about the stress energy tensor, which is how we relate density and flux of energy to the gravitational field and general relativity. We'll describe conservation and non-conservation formulas, and finally, you'll get to see the full form of the Einstein equation. That's the left and right-hand side. Enjoy. So Ben.
Hey.
Part 6.
Part 6.
General relativity.
We finally get to the core of the matter. So, let me remind everyone, and potentially it's been a little while, of what we're trying to do. This is where we finally get the full form of the Einstein equation, the fundamental equation of general relativity that tells us how bodies with mass should interact with each other. And the way that it happens follows this structure, right? Measures of space-time curvature equaling a measure of matter, energy, density, right? Last couple of times actually, we focused on this guy, and we were able to pull out the vacuum Einstein equation, and we were able to solve that for a particular metric, G alpha beta. We were able to get the Schwarzchild metric, and we got from that the prediction of black holes, singularities that break down our physics. That's really cool. It's now time to move on over and get this side. We need to talk about how and why one might be interested in measures of energy, matter, etc. Now, first up, we're going to have to talk about densities in relativity. Why? Well, we found that on the left-hand side for Ricci curvature, if you go back through that and look at the form of that equation, it basically depends on a bunch of derivatives of your metric. Now, an important point of derivatives, and all of those derivatives are with respect to your spatial coordinates. So, as far as the units go, that basically means a quantity divided by a distance or some other spatial metric, right? Spatial object. It could be a singular distance. It could be an area. It could be a volume. But those types of quantities, something divided by spatial measure, those are densities. And what we know about densities, what we know, since they rely on that spatial part in their denominator, we know that the notion of space has a wibbly wobbly quantity to it in relativity, whether it's special relativity or general relativity. The notion of how much volume or how much length or how much area there should be in a certain space changes based on how you look at it. So what we have to do, right? Basically, the idea of space is relative in relativity. So what we're going to have to look at is how does that affect densities when you're trying to calculate them. So the very simplest density that I could ever come up with is the density of a scalar. What's a scalar? Well, an example of that might be
pick a direction.
Pick a direction. I'm trying to get it to move, and it's like, no. A example of a scalar would most easily be a count. I count the number of particles that are there, right? That are in a box, right? So let's say here, that's exactly what we're going to do. I give you a box that's in space, and it's going to have n particles. So the number of particles in this box is given. N particles. Okay. The next thing that I'm going to say is that it has some velocity that's aligned along the direction of that box, right? Basically, you have your box so that a pair of faces are in the X direction, a pair is in the Y, and a pair is in the Z direction. and then you're moving along, say, the x direction. Okay, that way you don't have like weird shifts. It just keeps the math. It keeps the math relatively simple, straightforward.
Because it's a box.
Yeah.
Okay.
Okay. So we have some 3-speed specifically, right? The velocity is a speed in your space dimensions, right? We talked about how in GR, everything, no matter whether it's moving through space, has a 4 velocity.
Mm-hmm.
The components of which basically the time component is going to be your gamma factor, and then the spatial components of that 4 velocity is going to be your spatial velocity times gamma.
Okay. Yeah.
Your Lorentz shift component, basically. So space speed v. Okay. Now, let's look at the box in its own reference frame. So in its own reference frame, the box has a particular volume, right? It's the biggest volume that anyone in any inertial frame could possibly measure. And so let's call that big V, big mu star. Okay. So if I have this, I now have, in its rest frame, I have enough to calculate for you the density of this box, specifically the number density of particles contained in this box. Pretty easy. Right?
So does the density increase as the speed increases?
Well, we're going to get there. Let's just calculate what density is for this particular moment, this box.
Fine.
Which I'll call little n, and that's just going to be the number of particles divided by, your volume in your rest frame. Okay. Well, the next logical question, which you got to before I even could finish writing out what number density is, thank you kindly, sir, is what happens to the number density when you shift from a box's rest frame to a rest frame where the box is moving with a particular velocity, specifically, let's say, with the spatial speed v, right? Where I'm moving and I see it move along there. Since I've oriented myself so that the velocity is along in one direction and I'm, let's say, facing the box so it just looks like this. This makes the math relatively easy, although either way, the multiplicative factor is going to be the same. Along 2 directions, the directions that it's not moving in, no contraction happens. Along here, let's say, it's labeled, I think, x, right? There is a Lorentz contraction along the x direction. And that brings with it a single Lorentz contraction. Lorentz contraction coefficient? There we go. Remember words. And when I multiply all 3 of my new dimensional trackers, right, x, y, and z, in the new frame, and I do the Lorentz contraction across the appropriate variable for each, multiply them together, I get just one factor of Lorentz contraction to the volume of my box in this new frame where the box is moving. Or to put it in words, because it's much easier to actually see things right, is to basically say that in, let's call it V frame, the volume of the box is simply the volume of the box in the rest frame times 1 minus V squared to the 1/2, right? Your Lorentz contraction, which basically says, oh, okay, according as velocity increases and goes from 0 closer to 1, the volume of my box is going to increase. Now, relativity doesn't say anything about the number of things changing. So we say, in my new coordinate system, the number of particles m prime is just equal to the number of particles I had to begin with in its rest frame, right? I should still calculate and count the same number of particles. And so what that tells me is that
And just a rehash, that velocity has been normalized to speed of light, right?
yes, speed of light. That's why I said velocity goes from 0 to 1.
Okay.
Right. We've been using c equals 1 for a little while now. If you've watched any of these series, that's what's either natural or geometrized units. Basically, depending on how you set constants equal to something, it changes basically what different quantities are equal. So there in geometrized units, basically everything is measured in powers of length. All mass is length. All time would be a length. Yeah, it's good stuff. Natural units gives you like everything's in terms of energy, like different powers of energy. And for various applications, one makes more sense than the other. Here, geometrized units make sense because we're just looking at the differential geometry of this stuff. So I'll call that little n prime, and that's just n prime divided by v. And that's very easily just the original number density now multiplied by 1 minus v squared, square rooted. So as my as the objects that I'm observing increase in velocity, change to some movement, what I will measure when I look at them will be a shrunken volume, which, since volume's in the denominator of density, increases the density that I measure in that frame versus the rest frame. So just like how...
So the answer is yes.
Yes.
It gets denser as they go faster.
Yes. Things become more dense as they are moving faster to outside of observers, right? Now, we can actually define then this as... We can define a number current in four dimensions. This
A number current?
a number 4 current, which I'll simply say, okay, my number 4 current, which is in... I'll give it big vector. Actually, no. Let me do components in alpha just to do 4 current, so that we are consistent. Is a number times the 4 velocity. And my intuition is that this denominator here is the time component of my 4 velocity. And if I were to want to measure how many particles are basically moving through a, let's say, a 2D sheet, what I would do is I would simply say, oh, well, it's n time the number current times the velocity, right? The three velocity, spatial velocity, but this is just the spatial component of your 4 velocity. So I define this 4 vector in the same way that I define a 4 vector for velocity. The way it generalizes from 3 dimensions to 4 is simply that. This is actually an interesting... This is a typically actually general way in which vectors generalize. Like currents generalize from 3D
General squared.
to 4. General. Right. If the spatial components give me an idea of, okay, if I look at, say, a particular point or like a line in how many particles go through a particular sheet, right? It's going to give me this nice volume. because if it's got a velocity, I know the distance that it covers is v dt, right? Like in a certain amount of time. So this gives you this 4 volume that you construct to understand basically how many particles you would have in a particular 3 volume that has a time component to it. Why is this important? It might feel a bit abstract, but here, I'll get to it. Basically, that encapsulates, if I let my boxes and areas that I'm measuring get small enough, I can talk about this notion onto a basically define densities and currents at singular points in space-time. And I can vary how these particles move through, how the densities and currents change, but the thing they have to respect is that the number of particles is conserved. Right?
Mhm.
In physics, we typically see this written out. Say, for example, numbers. I would say, oh, okay, the time derivative of my number of things with respect to time, right, has to equal the spatial divergence of the number current, right? Basically, the current of the current that you get by having these particles flow through a direction in space, and that has to equal 0. If I use full GR notation, this corresponds to basically saying that the partial derivative of my current vector, my current 4 vector, or excuse me, number current 4 vector, is equal to 0. Okay. This is indicative of any conservation law you'll have. Basically, a conservation law is when I have the 4 derivative of an object equals 0. That tells me that that thing is conserved. This is how, and just like, right there, right? That basically boils down to this. And I can say, aha, whatever this quantity is, it must be conserved in physics. And these are always useful because these allow us to constrain different problems and different solutions when we're trying to find what function fits a particular setup. We have an equation. It's like, okay, it must fit this thing,
Right.
based on initial conditions that we have.
So what that top equation is saying is that if you do not have a source or a sink of particles, which is what the del dot n is, then the number of particles cannot change with time.
Right. Unless in that point the universe says, oh no, here's new particles. Here's
Unless
new
there's like a
particles, here's
white
new
hole
particles.
sitting right there. Or something.
Yeah. I mean, this is useful for fluid dynamics, right? If you're thinking about fluids, like a particular spot, if I have a tub as I'm swishing my finger through and seeing how the water moves around in response to that, the number of particles has to be conserved, except if I turn on the faucet.
Right.
And all of a sudden I've got a sink or a source wherever the water hits. Or I open the drain and then all of a sudden now I have a sink, right? Literally the basic definitions. They're so good. So densities in general end up being the time component of the 4 vector whose spatial components are the current density for that object.
Okay.
So basically, densities are fluxes in time-like directions through space-like surfaces, and currents are fluxes in the space-like directions through time-like surfaces.
Write that down. That's good.
Okay.
I like how we go from densities to fluxes.
Yeah, fluxes. Because what is a flux? The idea of a flux is that it's simply how much of something flows through an area. Let's get rid of that. Flux.
Nice.
And then current, which, like I said, flux in space-like direction. Through time-like surface 3 volumes.
Now, what's a time-like 3 volume?
Basically, a volume that I construct that dt is one of the directions of the volume. Basically, this object here. This here is as I've written it, right? Because one of the sides is v dt. That is a time-like volume there.
Okay.
And the flux that's running through it is space-like because the particles are moving in a spatial direction. The density, the time-like flux would be I'm looking at a particular point in time, and at time 1, I've got a big chunk of mass or charge, and then over time I watch the value of that shrink. Obviously I'm looking at a single point, so it's not physically the shape, but like the value of that charge goes down. And our conservation rules tell us, oh, okay, those two quantities, those two fluxes have to be related to each other in a particular way, particularly this conservation rule here. But yeah, that is basically what keeps this. Densities and currents are on the same level, the same thing in that they are both fluxes, in the same way that time and space are the same thing because they are the same, they're measures of space-time, right? They're components of distances in space-time.
Right.
Yeah. Now, here's an interesting consequence of the changes that density has based on which reference frame you're in. So this actually will show basically there is directly and concretely how there's an interplay between electric and magnetic fields, and kind of gives an illumination into, well, you can't, neither one is more fundamental, and neither one can be considered without the other. How? Well, let's see. So let's consider.
He's getting excited.
Oh, yeah. Am I getting loud?
Oh, yeah.
Oh, yeah. All right. I've got a wire. And I've got some electricity through it. And what does that mean? Well, it means I've got positive charges. Right. And for the sake of my life, I'm not going to write the other ones as balls. I just kind of committed to this. And I've got negative charges. Now, they're arranged in such a way that effectively, if I'm far enough away, this looks neutral to me.
Mm-hmm.
Okay. But I'm going to say that these negative charges are moving with some velocity. Just like how we have electrons moving when you have current in a wire. When I look at a wire, even when it's powering a device for me, the electric field that I feel is nothing. Right? The electric field that I have, it doesn't change. So what that means is if I place a positive charge outside here, it won't move. Right? I have it sitting still. It doesn't move. And in fact, if I do that in reality, also, I see nothing. Like, it doesn't move. There's no electric force pushing it away. Now, let's change that. Let's say that instead we have the same situation, but this test charge on the outside, this positive charge, is moving with the same velocity as my electrons. Okay. Well, what is it going to see? What are we going to see physically from this? The easiest way usually to do this, well, actually, okay. So from the outside, it appears that the electrons are still in such a way that they have the same density as the non-moving protons up top. So as far as I as an outside viewer observer watching this positive charge on the outside moving along at the same speed as the electrons on the inside, it shouldn't move according to my theory about
What
the
should
electric
move?
force, right?
I don't see electrons moving.
I shouldn't see this get pushed away. Sorry, I should see it moving. I've given it some initial velocity.
Well, in what scenario would it be pushed away?
Give me a sec,
Okay.
because we're actually going to show you how that's wrong. But as far as I can say, if I'm just looking at electric forces, I wouldn't see it move. What I would see is if there were an imbalance of the density of charges,
Yeah, it'd either
Right,
be
it would-
attracted or repelled.
it would get attracted or repelled.
Yeah.
So let's go to, instead, let's consider the frame of reference of our particle. So we now sit in how the particle was moving, right? Well, so this is the lab frame. And now we'll go to,
Bill's, can the blue be seen pretty well?
hopefully, I mean, it's done all right before. So what will things look like here? We have the same setup. I have my positive charge here. I have my negative charges, say, along the bottom. And now it looks like my positive charges are the things that are moving, right? Because they were staying still. They were staying still while the particle was moving, but now the particle is moving along at the same speed as the electrons. So it looks like my positive particles are moving in this direction of the same velocity as before. Now, charge is a scalar. And what we were just discussing is, well, the density of these positive charges, positive density, has gone up. Because since I see them moving compared to the picture where they were not moving, they've been Lorentz contracted in that direction. So they appear tighter together. Interestingly, the opposite is true for the negative electrons. Here, they were moving, but I had balanced them in such a way that their density matched the positive charges. But now that I move to a frame where they are no longer moving, their density decreases because they are no longer Lorentz contracted in the direction of the wire. So the negative density goes down. Okay. Well, what does that mean? Well, whereas here in the lab frame, I had perfectly balanced the density of the positive charges and the density of the negative charges, the addition of those so that they equal 0. Well, now I've got, colloquially, I would think that the E force would be proportional to the density plus minus the density minus. And it was balanced in the lab frame so that those two are 0. Well, now this has gone, the D plus has gone up and the D minus has gone down. Well, this becomes a positive quantity. So there is a positive E force, which means as far as this particle here in its own frame can tell, sees an electric force that pushes it away from the wire. So I've got an electric force here, but I don't have an electric force there. How do I reconcile? The thing that comes in to save our physics and says, no, you still see in the lab frame the particle move away from the wire, is the magnetic force, right? In the situation where the positive charge wasn't moving, everything was fine and dandy because the magnetic force requires positive charges in general to be moving to experience it, right? The Lorentz force FB, right, is simply is it Q cross QV cross B. The particle, there must be some magnetic field, but the particle also has to be moving in that magnetic field to feel any force. So what looks like in one picture magnetic force, in another inertial frame, looks to be electric force. And an important point, and Einstein gives in just general or special relativity to begin with, is that all inertial frames are equally valid, right? So there's no truer picture to say it's being affected by magnetic force or it's being affected by electric force. This illustrates for us that basically you can not untangle E field and B field from each other, right? On a fundamental level. I couldn't say whether one is more true or not. It's all depends on how you look at it. So it's the theory is, which is why we call it electromagnetism, because there's an interplay. They are part of a singular force, not just two different forces that can sometimes interplay with each other. And that all comes from the fact that special relativity causes densities to change. Even just scalar densities, like the count of charge.
So where's the but?
Oh, there is no but.
There's no but.
There's no but. It's just cool.
Okay.
The but was describing, saying, oh, there's E field here. How possibly could you have movement over here? Oh no, this density thing breaks down with reality. But actually, it's fine. Magnetic force comes and saves you, depending on the perspective but depending on the inertial frame you're looking at the physics from. People won't agree on what's causing what to move, whether it's the electric force causing the particle to move away from the wire, or it's the magnetic force causing the electric force to move away from the wire. But they will agree on the physics, that is, some electromagnetic force comes in and causes this particle to move away from the wire. No matter whether I'm observing the phenomena, sitting with the particle itself, or watching the particle whiz by me.
Now, why is the particle moving away from the wire in the top frame?
Because the magnetic force, because cross product, right? The particle is moving in this direction.
So the moving charges are generating a magnetic field.
Yeah, the moving charges in the wire generate a magnetic field
Right.
that the outside particle interacts with. Sorry if I am assuming a bit too much for
And then at the
where we've gotten
bottom,
in the discussion.
we also have the same phenomena.
Right. The moving charges change density, and that causes there to be an electric charge or an electric force. Right? What we distinguish as electric force, because the way that it behaves is not a cross product. It's a direct divergence.
Okay.
But those two phenomena, it turns out, are just ways to describe the same thing. It just what you will see changes depending on your inertial frame. You have to have both, which is what I find pretty neat.
Wow. And there's no third derivatives,
Nope.
tensors for GR, anything?
Nope. This was a nice, simple
Okay.
example. I know it's hard to believe coming from me that I'm just like, yeah, here's an example, and the basic physics falls out. It's really cool. To be fair, I'm not doing a research paper, so for once, finally, I can just be like, aha, this is a cool thing.
Impressive.
And for our viewers who may not be so familiar with E&M, we have a term for moving charges, don't we? Currents.
Exactly. Yep. Usually not single particles, but hey. Let us move down to the next thing. So, next we've seen how density changes for scalar quantities. But one of the important things that we'll never get away from physics is momentum.
Mm-hmm.
Momentum is not a scalar. Momentum has direction. It's a vector. And in order to do that, well, we finally need to look at what is momentum in special/general relativity. Hooray. All right. So, for those who are unfamiliar,
Is this where we're going to impart momentum to light?
not necessarily. Not necessarily. Just in general momentum. A momentum P is simply a particle's mass times its velocity. Velocity has a vector quantity, meaning that you now have momentum being a vector quantity. This is classical physics. So the question is, how do we generalize that to GR? Well, we already kind of learned that lesson. The way that you generalize things in GR is to take your anywhere where I see a 3D vector, right, 3D velocity, and replace it with my 4D velocity, right? So what I would define now as my momentum would be P alpha is equal to M for velocity. Okay. Well, to understand this, let's look at the components. Okay. So the 3D components, basically I can talk about my 4D with a bit of abusive notation here being a time component of momentum and a three velocity, a three vector momentum. Okay, pretty easily. The 3 momentum is just the mass times the velocity that's moving on, but now it's divided by a Lorentz factor. Pretty straightforward. Okay. The time component is going to be m square root 1 minus v squared. Okay. To understand, one neat consequence of this, right, if I do P alpha, right, the dot product of this thing with itself, what this gives me is that this is equal to negative m squared in geometrized units. There would be a c in there otherwise.
Okay.
To kind of understand what physically I might like assign these things, what things in classical physics these might map to, what I can do is I can look at the perturbation, the first order expansion of these quantities with respect to v, my velocity, when it's very small. So velocity is very small. So v much, much less than 1. My p vector is basically just mv. Okay? Plus higher order terms, which we say, since v is very small, go to 0 compared to your first order term.
Right.
Pt is close to m plus 1/2 m v squared. This is the lowest order term in v in that expansion. So that's the one you keep. Everything else is higher. For those familiar with physics, right, with classical physics, they might recognize this formula as the kinetic energy.
Mm-hmm.
And if we had geometrized units, we would have appropriate c in there to whatever the right power is. This motivates us to define our energy as the time component of your momentum. Kind of in a similar way that a density is the time component of a current, and a density is a static quantity, right? It doesn't spatially move. Your energy is a spatially static quantity for the momentum, which will take it away or to a certain point in your system, right?
Okay.
If I use this with this definition, right, with PT, what this pops out is telling me, oh, okay. Basically, if I replace this with E, this formula becomes E squared plus P squared equals negative M squared, which I can then, excuse me. And since it's a time component, it should have a minus sign on it. Important here. What that lets me do is swap these guys back and forth to opposite sides of the equation. And I get M squared plus P squared equals E squared, which I can take the square root. Right. Okay. And here's a fun thing. This, well, remember, P is the momentum, so it's attributed exactly to the velocity. If I have a particle that I have no velocity for, this reduces to E equals M, or if I weren't using geometrized units, would be
Right.
E equals M,
Yeah.
C squared. We finally did it. We got to that very famous equation.
Yeah. I knew it was coming.
Oh, God. I don't know. 200 hours in, and we finally get to the one thing that maybe everyone actually could recall about GR. This is how you get this famous relation. It's the fact that energy is a single component of your momentum, right? Everything has a momentum. It's just a question of how is it concentrated between the time and space-like dimensions. Just like how everything has a velocity of magnitude 1 in GR. And it's a question of what percentage of that is concentrated in the time-like direction or the space-like directions. Okay. So we're interested, and this is how we get through momentum. Now we're interested in how does, if I have a volume of space that I'm paying attention to, and let's say that volume might be moving through space or time, right? It's got its 4 velocity. How do I associate that 3 volume, which is moving in a particular direction, with the energy momentum 4 vector, P alpha, right? So basically, what I'm asking is, I've got some change in 4 momentum. How do I associate that with a 3 volume moving in some direction defined by a normal, right? Normal being the basically the dimension that is not included in the volume itself, right? Like if I've got a 3D volume, the only direction it could move is in time,
Right.
Right? A 3D space-like volume.
Right.
If I've got a time-like volume, so basically a 2D area, and then I'm looking at how things in time flow through it, the only direction that will matter to it is this third spatial dimension, right? So how can I basically complete this equation so that this is true? Well, GR, and actually let me do the right indice. GR tells me very easily that the thing that will take 1D object and give me another 1D object is a tensor.
Ooh, boy.
Oh, yeah. So welcome to the world of tensors yet again. And here, this guy has a very special name. This is the next bit. This is the stress energy tensor. It basically tells us information at any point in space and time about the energy or the momentum, or the stress of the system. So to see that, we're going to basically see what each of these components are based on how we split up our volume, right? Our 3 volume moving in a particular direction. So if I have a 3D space volume, what that means, so this is, that looks bad. If this is space-like, what that means is that in beta, or just do alpha to make my life easier, the components of that are 1, 0, 0, 0. It's moving in the time-like direction. And
Right.
yeah, so the only non-zero component is in sub 0. Well, that tells me what this can be, right?
No negative?
No, because this isn't a distant metric. This is just telling me I'm pointed in that. Yeah.
Correct. Okay.
But if you were trying to pick a space, yeah.
It's just the normal. I got it.
Right, like the 4 velocity isn't a negative quantity. Right, the time component of that 4 velocity isn't a negative quantity. It's just your Lorentz factor.
Right.
Still positive.
Yeah.
Same thing here. So what does that mean? Well, that means this equation then becomes, so let me give it a name. I'm going to call it 1. So then 1 becomes, well, still a momentum. So delta P alpha, but it depends on T to alpha time-like component, or 0. Right here I'm swapping back and forth, swapping between the index and the variable itself, and then that's multiplied by my 3D space. So now what this tells me is this is 4 equations, because alpha can range through 4 different values, right? It can range through T and the 3 spatial coordinates. So what I can look at is, let's look at the time-like component. So delta PT. Well, remember, PT, that's just an energy, which tells me that the tensor component TT, the very first, basically 0, 0, if I were to arrange this in matrix form, is simply energy divided by the volume of my box. What is that? That's an energy density, right? Okay, so the first corner component of the stress energy tensor is just energy density. Okay, what about the spatial components? What about if P is some spatial component X, Y, Z, or 1, 2, 3? Well, then I have that T spatial component time component is equal to just a change in momentum in a particular direction divided by a volume, or what we'll call a momentum density. Right?
Yeah. I mean, that's what
specifically,
it is what it is.
A momentum density in the direction given by whatever that spatial component is. Okay. And so that would tell you, if I gave you the volume of your box to multiply that momentum density by, that would tell you what is the momentum of this box in that particular direction, right? So that is basically the first column of your stress energy tensor. You've got an energy density and then a momentum density, right? Kind of like P, but the density of P, right? A spatial density of P. Okay. Now what we can do is we can look at the other.
So there's only 2 components?
There's only 2 classes. There's the time-like and then the space-like.
Oh, right. Gotcha.
Right. Technically, there's 3 of space-like.
Okay.
Yeah. Okay. Another thing that I could do is if I want to know what's the meaning of T alpha J, where J is then X, Y, Z. Basically, what are the other columns when you got spatial coordinate columns? Okay. The way to do that is the same trick that we did, except now, and actually, let me move this over here. Maybe a different section. Okay. Now, delta mu is time-like. Okay. What does that mean? Well, that basically means that time, a difference in time, is now included in the in one of the three things that makes up your volume. One of the three things you multiply, distances you multiply together to make the volume, and your velocity vector, the way that it's oriented, right? Like for space-like, it had to be oriented in time. For a time-like, it has to be oriented in the direction that is left out. So here, let's say that the direction that's left out is the x direction. So what does that mean? That means n alpha is equal to 0, 1, 0, 0. Okay. That means this would basically be a box. Well, here, that means delta p alpha is equal to t alpha in the x direction, delta y, delta z, delta t. Okay.
Just real quick, this convention is sticking to deltas. Why exactly are you using the deltas? 'Cause normally you would read that as change in something.
Mm-hmm. Because for a box, you've got a change in position.
Right.
So that's telling you that, like, as the box goes through somewhere, there's a change in momentum in that area.
Okay. So we are actually talking about just normal deltas. Okay.
Yeah.
Gotcha.
Normal, just change. All right. So now we do the same thing. We consider alpha when it's the time-like variable and alpha when it's the space-like variable. Okay. What does that give us? Well, tj ends up being delta pt, which is delta energy divided by a time, and then divided by an area.
That's a delta over on that P, but that's an actual A.
Yes.
Okay.
Let me fix my bad
Now
handwriting.
that there's a real A in here.
So that A corresponds to an area. What this tells me is that is the change in energy with respect to time through a particular surface. This is an energy flux.
Right.
Right? Well, but it turns out that
Well, change in energy flux.
right, an energy times a volume is just a momentum.
Right.
Coordinately. So this actually tells us that this keeps the symmetry of the stress energy. That you know now that the stress energy tensor is symmetric, which you would expect in GR anyways. But basically that energy fluxes are the same as momentum densities. So my first row, right, the spatial parts of my first row equals the spatial parts of my first column.
Okay.
Right, that they are the same quantity, even though I can interpret them as being different things, right? An energy flux versus a momentum density. The last piece then gives me, if I have what's T ij, well, that's delta P I delta T divided by an area. Hey, do you remember what delta P delta T is?
Delta P, delta T.
A change in momentum per change in time.
Oh, isn't that an acceleration?
Yeah, it's a force.
Yeah.
So this is a force over a changing area. So Tij is the ith component of the force per unit area exerted across a surface with a normal in the direction J. So what is that? Well, pretty easily. You can imagine that by imagining me pressing on this table instead of just straight down, but at an angle. And the stress tensor parts tells me the stress, right, produced by that. But to get the force, all I have to do is multiply by the area that I'm pressing in across either the surface in this direction to get the stress along the table,
Right.
or in this direction to get the force into the table. So I can tell you how much I'm pushing the table in that direction or straight down by looking at the stress that I'm exerting when I push.
So we literally made the mechanical
Yeah.
version of stress?
Absolutely.
Okay.
Yes. The mechanical notion of what a stress is. So here we go. This then, let's see if I uploaded the picture for this to make my life easier. Hopefully. Always hopefully. Yeah, there we go. Tells me, huzzah. This is what basically the coordinates of your stress energy tensor boils down to. You've got the energy density and the time component. The first column gives you the momentum density and the energy flux, and the parts that are restricted to spatial coordinates only give you a stress tensor. Basically give you a thing that when multiplied by an area gives you a force. Basically a force flux, right? That is what stress is. Is the flux of force, you know, given a unit area or something, right? All right. So that is our form of the stress energy tensor.
Pretty cool.
Yeah. Now, a neat thing about this is a neat and then perplexing thing, both, which is the conservation of this, right? In flat space-time, and here I'm just going to postulate it and say what it is without actually specifying and how we get there. But the form of the stress tensor is always such that the derivative of my stress tensor with respect to my coordinate system where I've contracted one of those variables with the stress energy tensor itself is equal to 0. This encapsulates the conservation of both momentum and energy in one GR equation. Right? One for velocity gives us, or for space equation, gives us the conservation of energy and momentum right away. Now note, this is a partial differential, right? Partial differential operator. And like the time component, for example, right? T component gives me energy conservation, which is basically just saying, you know, the derivative of my energy density with respect to time plus the divergence of the momentum density, which I'll define here as pi. That's what the notation does. That has to equal 0. When I go to GR, right? When I go to general relativity where you've got curved things, what we discovered that in order to any equation that you had to keep it consistent, to keep it the same equation, you have to take partial differentials and add in the specific piece that depends on your curvature. So what you have to do is no longer use partial differentials, you have to use covariant derivatives. So in GR, the covariant differentiation of the tensor is equal to 0. But here's an interesting thing, because this is what conservation of energy and momentum looks like, because there's another term here in the covariant derivative, which hopefully the audience can see.
Oh, I think I know where this is going.
Means that in curved space-time, energy and momentum are no longer conserved quantities. We no longer get to keep them on the same level that we had through all of classical physics. Instead, it no longer maintains and reduces down to our classic divergence conservation theorem there. Instead, energy and the energy of matter itself isn't conserved when there is dynamic space-time curvature happening around it. Instead, it changes in response to it. A classic example of this is the cosmic background radiation. Specifically, the energy that it provides, effectively the temperature that it gives us, we know is actually going down because the universe is expanding. The curvature of space-time is changing, and that reduces the energy, what the actual energy density is. No longer is, if you were to do classical mechanics, you would expect that the cosmic background radiation would always have the same energy density, and therefore any point in space would have the same temperature. We don't. We know space is getting colder. And that's like, you know, when you look out at what possible ends, what happens on long-term scales with the universe, that's one of the things. Is like, okay, maybe the universe stretches so far, you hit where everything reaches zero temperature, even though there's energy in the universe, right? Now, granted, you would still have heat death even if you didn't have expansion. You would just have everything reach the same temperature. But here we'll get potentially to zero. We don't know yet because we don't know the dynamics of dark energy, literally the whole name of it. But yeah. It's a whole interesting thing. So we now have the pieces that we need to talk about Einstein's derivation of his equation. We've got a thing that measures curvature. We've got a thing that measures energy densities, energy, stress, and momentum densities. So now we'll have to walk through basically a little bit of the leaps of logic that went through to get this equation.
Which equation exactly?
Einstein's full equation, not just the vacuum equation, but the full Einstein equation.
Okay.
What do I want to say? Now, this is talking earlier. This is one of those things that the exact form of this equation is something that you have to guess at and then look at your empirical data, look at what the universe does and see if it matches and follows that equation. It's just like how for Maxwell's equations, the form of Maxwell's equation is technically a guess. What you do is you say, does this form in a vector calculus match what I predict in reality? When I tell it, oh, okay, I took an electron and I moved it here. What does my meter read, right? What does the math tell me? What do I actually measure? Does the math predict the correct thing? The same thing here. We're going to have to stitch together the various objects that we have in GR in order to get a relation that we can then test against data and see, does it predict what I measure? So, one thing that Einstein kind of noticed is that the Ricci curvature, my R alpha beta, had the right indices as also my stress energy tensor, T alpha beta. And what he postulated basically is that, well, maybe they should be proportional to each other, right? Like they've got the right shape. They would affect things the right way, right? Think about when I have a particle, the thing that will change its momentum will be another particle hitting it, right? So stress or momentum flux tensor. But also, if I've got a particle in curved space, the thing that will change its momentum is the curvature.
Right.
So it's not entirely beyond reason to say, okay, they should be related to each other in some way. They are two things that affect the same quantity, specifically your momentum, or your momentum 4 vector, right? So Einstein had basically has a principle, specifically a principle of general covariance, which states that all laws of physics are to be expressed in a covariant form, or rather, all laws of physics should be expressible in terms of tensors. And the idea is basically, if I use covariant form or tensors because they transform covariantly, that when I do my transformations from one variable system to another, I'll get predictions that agree with each other. So covariant transformation makes things stick, makes things be consistent in a very nice way. So, this also then gives you a method for how any physical equation will look in a coordinate system, because what you can do is you can find how it looks in an inertial coordinate system and then transform the replacements, transform the form of your equation by replacing your flat spacetime metric with the general spacetime metric and your partial differentials with covariant ones. Right. Just like how we did with the stress tensor, like conservation of energy momentum was partial, but now in GR it's got to be a covariant. Right. And it's pretty intuitive to realize, oh, the metric becomes the actual full metric instead of just the flat spacetime metric. Yeah. So we start with the vacuum equation, right? Specifically, start with here, for the sake of notation, since I didn't write this out, I'm going to change from R alpha beta to just R mu nu. Right, just two different indices. It's not that crazy. What I can do, right? We had the full. If we recall, right. We have the full expression of the Ricci curvature when I contract it right up here. You'll notice there are 4 terms in it. What Einstein did is realized, okay, there is a coordinate transform that I can make where my metric, the determinant of my metric, the negative determinant of my general metric mu v is just going to be a nice unitary one. So a rotation, right? A Lorentz rotation effectively. And if I do that, what this actually becomes is a thing that only depends on 2 terms, specifically Christoffel symbol lambda mu nu differentiated with respect to alpha lambda, and then plus 1 cross Christoffel symbol. That has this contraction across it. And of course, it still has to equal 0. Okay. Now, what Einstein wanted to do was to define this more physically by talking about it in terms of a energy momentum tensor, which he called T sigma mu. What does that look like? Well, the way to get that is you multiply this equation by the inverse metric to get...
Does that say tensor?
Yes, it does.
Okay.
Who needs handwriting? Okay. Should hopefully help moving it here. So I multiply it by the inverse metric, mu sigma r nu mu. This gives me a partial differentiation with respect to x lambda still of inverse g sigma beta Christoffel symbol gamma mu beta closed plus k times T sigma mu minus 1/2 my delta tensor and t. And this should equal 0, where t is defined as t mu mu. The contraction.
Where'd the delta tensor come from?
So when I define, that will follow out from how I define this t. Okay? T, or kt specifically, k t sigma mu has to be equal to 1/2 delta sigma mu metric and curvature times curvature to be fair, I'm trusting someone else with the algebra on this.
Okay, that's fine.
To be explicit about that.
Somebody's already done it.
I mean, Einstein did it supposedly this way. Right? This is how I define my t. And then that causes, if I were to plug that in, causes it to reduce to this.
Okay.
Now, this is the energy momentum tensor. This T is the energy momentum of gravity. That's what he called it, as he thought. So like the gravity gives energy and momentum according to this particular curvature relation.
Okay.
What Einstein then said is, well, actually, matter being a component to stress energy should also contribute to this. So basically, Einstein said the next step to actually like derive my equation is to replace T with T sigma mu plus capital T sigma mu, where capital T sigma mu is that stress energy tensor that we had before, that thing that comes from matter. If I make that substitution basically everywhere in this equation here,
Right.
where I see little t, I replace it with big T. What I end up with is one more equation, which will take a little bit of writing. So sorry, everyone.
Now, just to be clear, you had the big T. What is that middle term?
This is little t.
Yeah, but it looks like, is he the exact same thing as the thing on the
is.
left?
Because you're replacing the energy momentum tensor due to gravity with the energy momentum tensor due to gravity and matter together at the same time.
Gotcha. Okay.
Okay.
Yes.
So you do this, the form of this equation then looks like this. Lots of little doodads and doohickeys, as I'm told the professionals in the field call it. Minus 1/2 delta. And this equals negative k, basically the same term, but now for just the matter parts. And I define capital T in the same way that I find capital T with no indices, the same way that I defined little t with no indices, which is to say, oh, okay, it is the contraction of my T upstairs, downstairs.
Okay.
Right. I basically set them so that they're always there, and that ends up giving me a scalar. Okay. Now, here's the fun bit, is that you went through all of this and said, okay, my Ricci equation should be satisfied, and I can talk about it in terms of a vacuum equation if I look at my energy and momentum due to gravity exclusively, what I call gravity exclusively, I can get this form of my vacuum equation. But when you go to GR from special relativity, because you're taking into account fundamentally gravity as being part of the curvature itself, it basically means that little t is no longer, right? Little t mu, sigma mu is not really a tensor. It doesn't behave properly. It doesn't behave like a tensor should in our general relativity. So what that means is it's no longer a valid piece of this equation. Right here, the intuition is, okay, I can have this equation just as long as I drop this invalid piece. So you simply say, okay, ignore that. And there we go, right? Ignore that piece, and what I end up with, right? This was expanding the left-hand side of this, the left-hand side of this equation. And what I can do is I can say, okay, I drop this and realize that this is just G, I believe it matches the indices like this, G mu V. And so what I can say is, okay, if I drop that and realize that this is just already the right-hand side that I had to begin with, I can say that G mu sigma R mu V must equal negative K T sigma mu minus 1/2 delta sigma, that's a terrible sigma, delta sigma T. And if I then hit this with the metric, right, that's an inverse metric on this side, I can hit it with a metric and that'll just cause it to equate to 1. If I hit it with the metric, I can say, aha, this tells me R mu must be equal to negative K, my metric that I hit both sides with, which was sigma mu, and times T, sigma mu, minus, where am I? Minus, minus 1/2 delta, what is it? Delta, nope, sigma mu. Am I getting lost? This shouldn't be that hard. But I actually know what this thing does with this term and with this term. It tells me this acts as a lowering operator on this guy, and that acts as a the delta function just swaps one index with another. So basically what I have is RUV equals negative K T mu V minus 1/2 G mu V capital T. Now, this is so very close. It's almost proportional. It almost tells you that my Ricci curvature is proportional to my stress energy tensor. But I got this little piece here. What do I do about that? Well, simple. I set mu and mu and nu equal to each other by hitting it with a what is it? A swapping, right? I hit it with the inverse matrix in such a way that causes mu to be result. Basically, I hit it with a G nu mu, right? Which will replace the nu with a mu, but put it in the upstairs. So then I'll end up with the right-hand side of R mu mu, which we always define as just its own thing R. So what this tells me then is I can say my regular curvature is equal to negative KT plus 1/2 in this metric. It ends, since it's the sum of a metric, it ends up just being 4 times k times t. Well, I can resolve that, and I can just say, oh, this is kt. R is kt. What this then tells me with a little bit of algebra is that R mu nu minus 1/2 g mu nu r is equal to negative kt mu nu. Now, some people will get fancy and call this actually, let's not do that first. Next, I have to ask, okay, what is k, right? Well, I know the Newtonian limit, just like how I did with the Schwarzchild thing. I can say, okay, when I reduce this down to a particular value, what is k? Well, I find out that it is negative 8 pi g. This is what makes things work out properly. And then people get fancy and say, well, this whole thing, let's just call it g mu nu. And this is how we get to the final form. G mu nu must equal 8 pi g t mu nu, or otherwise known as the full Einstein equation. And there we go. Yeah. You might have noticed this relationship between this particular set of R, because as I pointed out earlier in the Schwarzchild metric, that the covariant derivative of this is equal to 0. And it happens to also the generalization of the conservation of energy and momentum. It tells me that the covariant derivative of t mu nu is also 0, which gives you kind of an indication that, aha, this particular combination might just equal that particular combination. And when I take the covariant derivative of both sides, I get 0 equals 0. I've got a good equation. But yeah, this is the full Einstein equation. This tells you, based on any density of matter or charge, anything that provides energy to your universe, causes a gravitational, or not even gravitational, causes a curvature in space-time. It doesn't necessarily have to be massive. It could be a massless particle that has charge. That will cause gravity around that particle based on the energy of that particle just having a charge to begin with. And this is the fundamental. This is how we make any predictions that you want.
It's pretty impressive.
In theory. Yeah. Now, again, this is a beast of an equation, because now it's the inhomogeneous solution to a partial differential equation where, that might be time dependent.
Right.
There's nothing saying that has to be not time dependent. There's nothing saying that has to be not time dependent. You might have all four in general, you'll have a reliance on all four components in your 4D spacetime. Just nasty.
Now, let me ask you, if somebody wanted to have a little more fluidity with that raising and lowering of tensors and things like that, what field of mathematics would they be looking at specifically?
So the full tools of this is all included when you go through and do differential geometry, and also you need, before that, some linear algebra as well, right? Because what we're working with are, like when we're working with tensors, you're working with things that in general behave like vectors and matrices. Sort of. Sorry, all you mathematicians. But things that behave like vectors and things that behave like the close cousin to the vectors, the dual vectors, which we talked a little bit about in the math. Technically, they have a little bit of different behavior. The kind of object that, a mixed tensor will give you versus a double lower or double upper tensor will change depending on how you feed it, like whether you feed it a regular vector, a dual vector, a different rank tensor. And it can get all complicated. usually, like, we went through this book, just Gravity by Hartle, and the math and exercises to get comfortable with raising and lowering tensors is all included in the book itself. And that's an important thing. Like, because GR doesn't need to worry about doesn't need to worry about some of the specific distinctions between vectors and dual vectors.
Mm-hmm.
Learning that might get in the way of your ability to get to doing this stuff faster.
Okay.
Right. So I would suggest an undergrad book in general relativity, because yes, the mathematics will be just differential geometry. But differential geometry is not limited to the 4D spacetime that we appear to have.
Right.
Right. So you might learn
Get more complicated.
things that like have conventions that either are more complicated or don't obviously directly match to this. Like learning about curvature and differential geometry, right? Like the Christoffel symbols, the way they come out, they're just like, oh yeah, that's a thing. And then you kind of move on. You don't actually use it depending for the questions that mathematically oriented differential geometry is interested in asking, at least asking its undergrads, right? Like there might be particular realizations that people go, oh yeah, no, we need to know this. But as far as like a book will ask you, it's not going to directly map. You're not going to do raising and lowering operators in a differential geometry book, even though you learn technically the tools necessary to do that. Right. But that's always how physics and mathematics kind of breaks, right? The distinction between needing a particular realization of a tool set versus understanding the entirety of a toolbox, right?
Yeah.
One of the most direct things, like GR, yeah, you can see it a little bit. It's
once
a little
you
bit
know
more,
you need a hammer, it's your skill with swinging the hammer that
it's
matters.
a little bit more like direct. The most obvious example that I know of where things break down between math and physics of like how you represent is group theory. Like what group theory even is for a physicist versus what group theory is for a mathematician are two incredibly different sets of thought and tools and questions that you're even asking. Because for a physicist, we know that reality only respects a few certain groups. And then you look at how you can represent those groups in particular dimensional representations. A throwaway line here that I don't understand fully the mathematics is that you know that there are 8 gluons because the SU2 rotation group in a particular realization requires 8 dimensions. And that's how you go, oh yeah, I got 8 particles. I think those are the right particles in the right group. Please don't crucify me if I got that wrong. Like the point is that like there's a structure of how you represent this fundamental rotation group that causes you to know you have a certain number of particles in your thing.
Gotcha.
But a mathematician is like, what? I don't care about SU2. That's just a rotation group. Okay, you've got rotation groups just all fit into this class. You have, there's rotations on any dimension, but let's look at now also the groups of permutations or the groups of, you do all these classes of different types of transformations. And you're interested in that. And like, it gives you interesting stuff. Group theory is effectively what gives you Galois theory, which just talks about something as abstract as like how you can put together finite groups of polynomials as families, and then the breakdown of those groups then tells you, oh, you can't solve 5th order polynomials or greater in terms of radicals. There's no quadratic formula for polynomials order 5 or above, which is, but like, and the question that those two aspects of the same thing, group theory, that physicists and mathematicians are asking, wildly different. So if you're interested in doing physics, it's useful generally to have a physics books. If you want, and here's the nice thing, if you want to understand how the physical theory looks in the fully properly done mathematical form. There is a physicist or mathematician who is interested enough in what that looks like to do the derivations of everything in the full, hard, painful way where you're paying attention to all the details explicitly. It's harder to read because the formalism of that gets in the way, but it's there. So yeah, that would be my suggestion.
Very cool.
Yeah. All right. So just to wrap up, we got to the Einstein equation. Next, we are going to look at a bit of an approximation, how if you have a source and you have a source that is far away, so your gravity looks not quite flat, but with a little bit of curve, just a little bit, how that can give us the gravitational waves that we were able to detect in 2015. I'll see you next time.
Very nice.